Okay, here we go. This is my first YouTube video posting of my first attempt at a Stjorn magnetic motor replication, somewhat modified. As you can see, we have a rotor here. Spins very nicely. Built out of a DVD disc, actually two of them, pancaked together, with magnets glued on the outside here in a horizontal fashion rather than the conventional axial north-south orientation. We have we get a light here. We got the toroidal coils wound on ferrite cores, special ferrite cores that I ordered with a extra high permeability factor, and about 12.5 meters of 23 gauge wire wound on that, which was a chore. It was quite challenging to do the first one. Second one went rather well and quickly. Over here we have red meter is the measuring voltage, yellow meter over here measuring current, power supply over here, just a standard PC power supply, using the 12 volt power 12 volt output. And I don't know if this power supply is actually, working quite right, because it keeps floating up quite high. It actually goes as high as 19 volts, but usually when it's, when I first turn it on, it stays below 12 volts, but if I leave it on and not run the motor for a while, it'll float up to 19, and it'll tend to stay around 17 once the motor gets running. Let's see, down over here we have the drive control circuit. Behind this little post here, which you can't see because I'm not going to move the camera there just yet, and you might not even see it after the video, or throughout the video, because I can't bring my camera back here. There's a sensor for the magnets and another toroidal coil like this one. Same configuration, same number of winds, same wire gauge, blah blah blah. What else is there? That's about it. And I think the coils are cooled down enough because they get hot when I forget to turn the power supply off, because my old Hall sensor which used to default into the off position, and this one seems to default into the on position, so if you don't turn the power supply off, it'll overheat your coils, and when the coils overheat, the motor just doesn't seem to run very well. Motor runs in a counterclockwise direction for the best. It'll run either way, but best configuration is counterclockwise as far as current draw goes. So let's turn it on. Initial startup is kind of slow. Actually really slow right now. Seems to be the time of day, believe it or not, makes a strange difference in how fast that motor runs. Right now it's not running really fast, so I'm going to get it going with a little trick here. Actually, you know what? That shouldn't be going that slow. It should be running quite a lot faster than that. Well, you know what? Let's just make it go really fast. There we go. There we go. Let's get her going. Alright, so we've added a little external device here that is somehow adding kinetic energy into the system where none existed before. We're looking at the voltage at about 11.04 volts. Current is steadily dropping. It's currently at about 1.12. I think you can see it on the meter there. Yep. Voltage over here. I'll move the camera a little bit now. We've got 11 volts there, 1 amp. So we're looking roughly at about 11 watts. And this baby's humming along pretty good. And let's put that little device in there a little closer. We're getting a little bit more juice out of it. Okay, so looking along pretty good for 11 watts. Now, let's get out the big guns. Here come the big guns. Okay, we have still about 11 volts. We're down to about 0.76 there, 0.75. Drawing on amps, so we're down to whatever that is, 11 times 0.73 for watts. It keeps going down, as you can see. The faster it goes. As far as RPMs go, this is probably about 2,800 RPMs, 2,700. And it can still go faster if the system is optimized properly. It all seems to boil down to sweet spots. There we go, a little faster. 0.7 amps. 11 volts roughly, 11.1. And we'll watch the spin down now. Here we go. You can hear the noise. It was moving quite rapidly. And it's going to spin down because I still have the power on. It's going to spin down to about, actually it should have stayed running at about 1.6 amps, but it looks like it's going to spin down further than that. It might stay running, I don't know, because I went to the store for beer and left it running, and when I got back it was still running, but it was very hot. The coils had overheated, but it was still running. Yeah, okay, it's stabilized at about 1.6, which is where I expected it to do, at about, yeah, 10.9 volts. It'll stay like this for a while, and then it'll probably eventually wind down due to the fact that the magnetic sensor should be adjusted for position adjusted, you know, for the slower speed to ramp it back up again. Like I said, it boils down to sweet spots. So we'll do it one more time. Okay. Let's pull out the real big guns. Here comes. Oh, hold on. Pinch. Ouch! Oh, ow! Ow! Sorry about that. Had a little magnet accident there. Here's the big guns here. Big 2-inch neodymium. 2 of them by 1/2 inch. $11 volts on the voltmeter. Coming a lot further down on the amps very quickly. Power increasing, speed increasing, amps decreasing, or wattage decreasing. Let's bring it in closer. It looks like we've topped it out, maybe. Nope, here we go, back out a bit. Another sweet spot. I wish I could get the tachometer on this so you can see the RPMs, but I can only have two hands. Alright, so we got 0.63 at 11.1 volts, which is probably about between 6 and 7 watts, maybe a little higher. So this thing's got a lot of torque for 7 watts. Then the spin down again. Okay, this time we'll shut the power off. And we'll watch her spin out till she dies. Zero volts, zero current, still spinning like the bejesus here. This particular rotor has 8 magnets on it. I have a rotor with 6 magnets on it that does nearly as well. This one seems to be a little bit more balanced. A little smoother running, as you can see, because it takes a lot longer to spin down. And it's still going. It's coming down to the last little bit here, probably at least another minute. And there you can see, yeah, okay, there's the other toroidal coil and the magnetic sensor. That's not the optimal place for that sensor. Well, it is for this particular disc. It's actually fairly optimal, but it can be even honed better. And that's, I don't know, that's about it. Still spinning. So for a Steorn design, this thing really cranks out a hell of a lot more RPMs than theirs ever did. Even without the external application of the special tool, which is just simply an external magnetic field applied from the outside. And I'm just going to stop this because it's almost done. Actually, I'm going to watch it peter itself out here. Alright, she stopped. Okay, so there's the rotor, there's the coils, the Hall probe on the side there, which is not really in the optimal spot, but optimal enough so that I can do the hands-free thing here. And the drive circuit again, which is just a simple transistor setup to drive the coil. And I think that's about it for now. I was going to do something else. What was it? I think I'm done for now. It's probably long enough for a YouTube post. Until next time, we will keep you posted.